Hello everyone. Today I will be talking about transformer. It was developed published in 2017 and it is the reference for all kinds of LLM architectures that are being used today. Without delay, let me begin the presentation. So this is a transformer. As you can see, this is the paper that I download from internet. So these were the authors. Now the main point about so let's just focus on the paper for basic, and I will begin with this core implementation. So what so they developed this transformer in order to do the translation of English to French or English to German, and they increase the British score by 2, and they obtained 28.4. And the main point about their transformer architecture is that they don't use CNN or RNN. They only use attention mechanism, and so since it is parallelizable and requires very less time to train, it is being very famous and very widely utilized. And the other parties they state that the RNN, which requires serialized man kind of training procedure, because for HFT we need HFT management state. So for that we need to wait for some previous computations. This precludes parallelization, so we cannot parallelize anything in the RNN. And so the background is they discuss about the background. And the model architecture is very simple. What they are telling is that so there are some input, and uh, there's represents z and z2. So in input this is encoded to z, so x is converted to z, and then the z, which is called the context vector or continuous representation, sometimes called context vector, then that j is then passed as a decoder, and it would give the output. So it is autoregressive, means it is using the previous output of itself to uh, predict the next, which is kind of like called teacher reinforcement mechanism. Alright, so I think the screen is visible. Oh, okay. Sorry, I had to do this. Okay, now if you can see the architecture, it is very simple. So we have some inputs, some sequence of inputs that is embedded, and the text are converted into numbers. Since this is for only text NLP, I will be talking about the text, but we can have some images, videos, everything as input and output. So it's kind of sequence to sequence tags. For example, the text is a hello, WhatsApp kind of thing, and that's converted into embedding, which means number 1 2 3 4 5 kind of thing. Then we need to add a position. So the hello should come first, hello, how are you, how comes second, and kind of that. So positional encoding is sinusoidal. So it's kind of since the sinusoidal is increasing, decreasing, increasing, decreasing, we can utilize the property. And then I will talk about this in depth in implementation part. And so this input with addition to positional encoding is then passed to self multi-head attention, which is kind of self attention but applied over h number of heads, which is kind of having to say that I have instead of having one head, let's have 8 heads. So it kind of gets it kind of different thing, and that is get concatenated. So kind of parallelization and concatenation, and then that is RNN, which is the residual connections, and this is the normalizations. It is post normalizations. So in some paper they found that normalizations at the initial state over here would be better, and that's called pre-normalization. So this is a best post normalizations that not best but layer normalization. So the neurons variance and mean are used to normalize the state over here, and that gets passed to this part. So there's some detailed comparison between Bayes normalization, weight normalization, and layer normalizations, of which I will be presenting paper very soon. But let's just say that this is after this thing we are adding residual connection and then normalizing this. This is layer normalization. Finally, we pass through feed forward, which is just a kind of a two neural network, two hidden layer or two linear layer stacked back to back, and that kind of so we can see it's just a mini brain, the self attention mini brain, and that gets also added. So basically, and this is an stack. So basically, the first gets input directly and attend over it, and then feed forward it, kind of pass to some small brain, and then there's n for the second encoder, which is exactly like this. This gets input this input from its previous encoder. So it's kind of like RNN, right? So it's kind of getting the input from previous layer, previous encoding layer, and then it is again passing to mini brain and then passing to the next encoding layer. And the next encoding layer, which is same as the previous, takes the encoding output from this previous layer and then do the same thing over and over for up to n times, and resulting that kind of same like RNN output or this transformer encoder part output is passed to the decoder over this context vector part. This is called multi-hit attention. This is cross attention because we are doing the cross attention, but decoder is somehow different. Only thing different is this part. So it is the same thing, but we are shifting right. Shifting right means we are shifting right means hello, how are you? So we need to say that given start of sentence, it should predict hello. Given hello, it should give how, kind of auto-regressive manner, and we don't do that in a sequential manner. In RNN we would do that in sequential manner, but here we just need to shift right and then send in one shot, so it it auto understand it because we are masking that over here, max self attention. So we don't see the future, but we can uh, predict. We don't see the future, and we need to predict that in parallelized manner. So anything that is converted to number, added some position value, and then attending max self attentions. Remember, there is a maxing over here decoder, but not in encoder, because decoder needs should not see the future outputs, future value. You just need to see the present and past, up to now, up to and above, up to and before, and same as add and norm. And then that output, if you can see, is passed as a one value, and the encoder output is passed as a two value. So you can see this can act as a query. This can key and value. So there is some query key and value. So query key value, query key value. So we need for attention we need three things: query key and value, query key and value. So it is kind of self attention. But here is one is passing from the decoder, but the two are the key and values are passing from this encoder output. And then next is similar, so we do the cross attention and then add the residual, again pass to mini brain, and then to the interesting thing is that this is done for the n time. For the second kind of input, what are we doing is that uh, it is getting the previous layer output, and then if you can see, this is done for n number of times, right? So this is for first time is this, and same thing, the output of this is passed to next part, and then this is done for n times. So number of encoder and decoder block is same, and finally the output is passed to linear layer, and then softmax and output probability. So in order to understand this, they have detail. Now, so first now let's understand the attention. So there is a scale dot product attentions. There is a product and summation kind of attention, and they have utilized product because addition would not scale to large number of dimension, and so that was the reason for choosing the scale dot product attention. Now if you can see, but the drawback of attention is that when we do multiply using this scale dot attention, the output, the multiplication and the result would be very high, so they need to scale it, and that's the scale part over here, and they scale it by dividing by some value the dimension of the vector, square root of the dimension vector. So what happens is that we have some key and query. So query and key, you can see that query and key are passed to matmul, which is matrix multiplication, and each query acts each query does multiplication to each key, and then query key. So it's kind of, this is a two-dimensional vector. So the row of query, the row of q is each query, and the row of key is each key. Since we cannot do that row by row multiplication, this key needs to be transformed into column wise manner. So in that manner, the row is query attends to each key, and similarly second row first column. So in that manner, right? First row first column for the second item, first row second column. So kind of like query key, and since it is a matrix form, so we can do in one shot one matrix multiplication. That is scale means normalized kind of thing, and then mask means if it is a decoder we need to mask it. If it is encoder, it's optional, it should not be, so that's why it's the max. So what happens is that masking would make something 0. The future value would 0, and that's why since the future value would 0, or let's say the softmax gets a minus negative value, which would mean softmax would get 0 value. I mean to say masking would produce softmax output to 0, because softmax, when it's very negative, it's provide 0 value. So that's why the softmax, to pass to softmax, before we need to max that into negative infinity, and that would get softmax 0, so it is not attending the future values. And finally the softmax and the b values are matrix multiplied, and then the output is the scale dot product attention. So same thing if happened over as number of heads, then is called a multi-head attention. So this value is blocked in as number of heads, and these things are passed to 3 number of heads. I mean to say these are passed to 3 small brains, or let's say here h is 3, so that's why 3 value over here. So v is passing to v is kind of divided into 3 linear layers, or 3 kind of small brains, and they are passed to 3 individual scale dot product attention. So it is a parallelized task, and finally we need to concat it. And concat means we get the same sequence length as before, but here the sequence length gets divided. Is it sequence length that gets divided or what? No, it's the input that's divided into number of heads. And finally we need to pass to the linear layers, same as before, and this is multi-head attention. So the scale dot product is very simple. It's given QKB, we need to pass the softmax over here, q into kt square root dk. So this is the scale dot product attention. So since the dk is the dimension of this vector, and if it's very large, then this kind of their assumption is that this would not explode it, and the softmax does not get value that is very close to 1, and then this is the b that is kind of in attention layer. This is kind of simple attention mechanism. So the physical meaning of this would be each query needs to see how similar it is to the key, query and key, and then softmax would compute the probabilities, and then the value would multiplied with that probability. So given this key and value pair, how the query attends to them. So for the self attention, q, k, v all are same. So I think this just need to memorize, but one can understand this as a self attention layer. So they have chosen this thing, and as I previously before, to reduce the pushing the shortness function into regions where it has extremely small gradients, means just you can see in the 2 dimension is a slope, gradient means slope, and which is a value near to 1. They are scaling it by dividing by this, or let's say multiplying by 1 by square root of decay. Finally, the multi-head attention is done in order to do what is called as this. Multis allows the model to jointly attend to information from different representation services at different positions. So in a simple sentence, they are passing to multiple heads, so that each head can get its one answer, and they need to concat it, right? So attend to from different representation service spaces. So if you can see, the dk and the dv are same, equals to, and they have chosen is to be 8, the number of heads is 8, and d model dimension of model, I don't know, but this dimension reduced to 64, and square root of this 8. Now if you can see the weights value, each query weight is transformation from d model to dk, a linear layer, and same goes for the key value. And once you multiplied query and the key is transposed, right? So we get a d model into d model, and finally when we multiply to b, there is d model into dv. Finally we get the d model into dv output. As you can see, d model into d model, and this as times of dv is actually d model. They have just for the sake of brevity, or let's say understanding, the as times dv dv is what, d model by h, and multiplied by h remains the d model. So actually the h times dv is basically d model from this representation. So the output is d model into d model. The same goes into input. There is no repeat. So the input is d model by d model. No. Input requires sequence length and etc. So leave it. Now, so the main thing is we need to understand is here. There are three kind of thing we need to understand. For the encoder decoder attention layers, the queries from the previous decoder layer, and the memory keys and values from the output of the encoder. So the queries from the previous decoder layer and the memory keys and values from the output of the encoder. This allows every position in the decoder to attend over all position in the input sequence. This mimics the typical. Okay, so I will come back to this shortly. And the encoder is self-attention layer. Values and queries from the same place, the output of the previous layer in the encoder. So values and query are key value and query from the same place. Each position cannot all position previous layer of the encoder. So basically the previous layer we should understand. In addition to input, we are also getting the previous layer as well. Finally, the self-attention layers in the decoder allows each position in the decoder to attend the positions all up to and including that position. So they are using masking thing over here. So there are three attention. Right now I will show that from the diagram. So attention 1 is this, attention 2 is this, attention 1 is this, as in there, 2 is this, 3 is this. So main thing is understanding this part. So for each kind of so whatever, so this is same, the output of the encoder, this kind of memory is same, but this part gets changes as n varies from 1 to n. For the n equals to 1, this is same, this is the pure input that's passed to a max attention, and then do the cross attention and to pass. For the n equals to 2, we are getting the output of it in here as query key and value, not the input. You should remember that. And then we are getting the for this attention, we are getting the encoder output same. So this remains same for n equals to 1 to n, but this value gets changes. So for n we are getting pure input, for n equals to 2 to n we are getting the output from itself, all outputs, previous outputs. Very simple, right? The implementation is very tricky. I will come back to that shortly. So the position wise feed forward is there's one neural network, one linear layer, and that's passed to ReLU, max of 0 or that. Finally the second linear layer, and very simple. They have used base model for the dimension of the model to 512, and DIFF is feed forward. So DIFF could be this thing which is 240. I'm not sure, but DIFF is feed forward. Okay, so maybe this is the 2040. So it doesn't matter. We are just using the two back-to-back position linear layer. Simple. That is called the position-wise feed forward networks. There's embedding and softmax, and this is embedding means convert text to number, and softmax is the probability. They are talking about this complexity. Now if you can see, the self attention is n square times d, recurrent needs n times d square, sequential operation. So this operation operates in O n, and this needs n o n, so number of sequence. This is the dimension, representation dimension. So if you can see a recurrent layer, if the dimension is very large, this becomes very complex. But since the sequence length always is less than dimension, we can have sequence length such as a sentence. I think, so let's not compare NNN, but we can compare the D. If we can compare the D, the recurrent layer is D square, so it's very complex, and also it requires O logarithm of, O simple n, but requires symbol constant O1, and path length is similar. Now they are considering the convolution over here, and convolution requires k is what? K is kernel dimension. So for each k, for each sequence length, for each dimension is square, and it's very heavy operation. But we can see this is doing in O1, and for computation minimum of sequential operation for 4 different layers. So if you can compare simply in simple manner, we can see the self attention is very superior to all of these if all three factors are combined. And the position encoding, as I have said previously, for the even part we are doing what? We are doing the sinusoidal sine function. For the odd part we are doing the cos function, and this is if you can see, this is position, whatever is the position, divided by 10,000 raised to the power 2i. So this is best illustrated in the graphical form. So if the I is equals to 0, we can see this is just sine function and cos function. So one is sinusoidal, one is cosine function. But what differs is that this I value and pose value, for each pose and for each I, these two are parameters to this function, but this d model remains constant. So for each changing value, this increases the angle value. The position, as position changes, the angle value increases, and since the angle value increases, it fluctuates between in this manner, 0 to 1, again 0, -1, 0. Does sign have -1? I forgot. Yes, it has -1. So yes, it is -1. For what value? I don't know, but sign is -1 also. Finally, for the cos, as angle increases, this value kind of works in a repetitive manner, and the role of this 1000 raised to the power this is to divide that angle. Simply, the angle division is same for whatever is the value of I. What changes is the sine or cosine function. So for the same value, for the same position, if I is odd, then that is sine value. So alternative kind of thing. And they have chosen this function which is variable so that it can accommodate to large number of sequence length. So this is the wavelength from a geometry from 2 pi to 1000 2 pi, and they hypothesize that it would easily learn to add it into relative position, since for any fixed k can be written in the linear function of p pose. So and using the learned also from the fixed kind of thing, they are linearly identical, so it does not matter, but they choose this uh, for the longer sequence length. Okay. The cell pattern is for complexity, path length. Path length would benefit these long range dependencies, so it can attain to future a value that is very distant from itself, and there is also differences of parallelization. Okay. And the training, they use this dataset WM 2014, and they trained it for 12 hours. Optimizer. So this learning rate is this is very complex. So this value is constant, but if you can see this minimum of this and this is very simple thing. So they are increasing learning rate linearly to the first one of steps, and then decreasing it thereafter proportionally to the inverse square root of, and then they are so first this function would be minimum, and then second this function would be minimum as from this, but let's not visualize this as this kind of learning rate of warm-up has been outdated by using post linear normalization, layer normalization, no, sorry, pre, and this was outdated, but they use this learning rate. So simple, first increase then decrease, first increase then decrease, simple thing. Okay. Now the regularization, they improve this some dropout and level smoothing. So two kind of regularization, very complex to pronounce. Now the comparison is very simple. So their model is superior in terms of big, but small also superior. But for friends, you can see 41.8. Finally, this is superior. Okay, now let's move on. The machine translation model variation. So they changes. So they change number. So for the case A, what they changed was the number of heads. As the number of heads got increased, the dimension of the key got decreased. Same goes for the dimension of the values. Same goes for the dimension of the queries. So as the number of heads increases, we split those numbers into each head, so they each get smaller values. So 32 kind of heads each get 16 values, whereas single one head would get 512. Simple, right? And as the number of head got increased, let's understand blue. The blue is higher is better. So 24.9, 20 it got increased, and finally got decreased. So there is kind of optimal value, kind of convex structure. And then they try to change, they try to so this one is, so when the key dimension was increased, the vector dimension was increased. As the vector dimension increased, the value got increased. Finally, this is basically because the bigger the vector representation, the bigger the representations. This is very clear. And then for the third experiment, they now change the number of encoder layer from 2, 4 to 8, and then you can see as the number of encoder layer or decoder layer changes, this value gets increased. See, again, it's the more dense the architecture, the better is the result. And then they try to change the dimension of the model, and this is kind of effect of this changing. So if we can if so from this to this it gets increased, and from this it gets increased. So basically, the higher the sequence length, or let's say higher the understanding of the model, the embedding dimension or whatever the D model, better is the result. So better, and then for the DFF, same goes over here. More complex model, more bigger, more better result. And this one is what? So if we have some regularization, it gets increases. So regularization is better thing too. And then but for this fixed positional encoding instead of sinusoid, they found that it is comparative to previous results. And finally, this was the big model, which is 628, and then this is the best model up to so far. And model parameters is 230 million params. And anything else? And they try to do on second data set too, so that the same architecture can run to different kind of use cases, and they found it to be superior in that too. And is there anything else? So attention visualization. So symbol is its application B. So it is kind of self-attending. This bold means the attention value is better or bigger. This is what we are missing. This is what we are missing. So kind of thing. Now let's go on to the implementation part. For the implementation, let me make it bigger so that it becomes okay. We are importing it, shading it, random value. Now the position encoding is very simple. So first get some zeros value of dimension max length and dimension of the model. The max length is sequence length. The model is the encoding dimension. Position is from in case of sinusoids, we are just adding sinusoid value, but position means 1, 2, 3, 4 like this. Okay, so 0 to this, and on squeeze means kind of adding one extra dimension. And a deep term is, so if you can see, this is the exponential. Since this is from mathematics, you know that a raised to the power x is same as e raised to the power, e means the e epsilon value, e raised to the power x, and then logarithm of logarithm of a. So e raised to the power So x, which is a raised to the power x. Okay, so we are supposed to do 1000 raised to the power this, and this is same as a to a raised to the power x. So finally this is same as ex, the actually it is in the power form, ax ln a. So e raised to the power x, the x is what, 2I divided by d model, and then multiplied by logarithm of a, this value. And then for the odd, for the 0, this is start from 0, go to the end, and step with the size 2, and for each of those pass the sign function of position and the deep term. For each data, for each column start with 1, go to the end, and then finally step by 2, and for that position go use the cosine function. So 1 2 kind of thing, on squeeze 0 would do what, it would add 1 as the base dimension, and finally it is registered as a buffer. It's not learning parameter, it's some constant value, it's buffer. And when we do the forward, it should do add itself to position encoding. The position encoding is so since it's a constant, we just need to index it, and so whatever is the base dimension, grab that, whatever is the d model, take that, but sequence length should be same as the x. Okay, finally we are passing the dropout, that value, and this is what positional encoding is. And vesicle dot product attention as from the paper, this is simple thing. Okay, so it is receiving query key value, and max is optional, dropout is optional. So these 5 are parameters, and the dimension of key is same as the query dimension, first dimension, and sorry, the last dimension, the number of vectors. And scores is query key transpose. So this is k dot t, transpose of this, and divided by square root of tk. Very simple, right? So this transpose is required because each query needs to attend to each, I mean to multiply to each query. So first row, first column, second row, second column kind of thing. Had it been just k, it would not make any sense, because it would attend to multiple queries, multiple keys. So each query, multiple keys, that would not have make any sense. And if the max is there, then we need to max fill. And if the max fill is works like that. If the max is 0, which is kind of true or false. If it is false, then we need to fill with a very large negative number, similar to infinity negative unit, so that the softmax function would give value 0. That is, it's kind of not attending to that value. Not as nobody softmax of that scores if there is a max, and then apply the max. Finally, if there is no dropout, if there is some dropout, then drop out some value. So dropout of 1 means make all 0, dropout of 0 means make nothing 0. So it's kind of probability of making some value 0 and some value not 0, and it's just for training purpose. And they are finally the attention weight is multiplied to value vector, value matrix, and the return is output. This is for just visualization purpose. Now the multi-attention is very simple. What happens is, we are having 3 small brains, the q, k, which are learnable parameters, and simple. So we are taking the same 5 values. So sorry, the 3 values, query key, 4 values, query key value, and then finally the max is optional for. So batch size is batch size. And now let's see the very thing is over here. So what happens over here is that we are passing the entire query to the entire WQ matrix. This is not matrix, this is some layer, the linear layer, and that is that's view is permuted in this form. Keep base size same as before, keep this self dot dimension of query same as before, this same as before, same as before, but we need to split this into number of heads. So, and sorry, the batch size remains same, the -1 will be filled automatically. This value was previously, if you can see, this value was so we had previously batch size, sequence, and the model. Since d model need to decompose into number of heads into decay, so we are decomposing that into two part, and the sequence length remains as it is. So we are just decomposing into two different parts, and the transposition the transpose is required because we need sequences in the second part. For the self attention, this scale dot product needs sequence length as its second parameter, second dimension. So for now, the sequence length at this point, sequence length is in the this third position, first, second, third position. So we need to permute this, transpose this 1 and 2, this and 2. So 0, 1, 2, 1, and this is transpose, so that sequence length becomes in the second part. I mean to say here. And then finally, these are passed to scale dot production, so these are get attended, and this would be, this is parallel syntax. Finally, this attention output which had received in the form of as expected, but we need to transpose that into 1 and 2 form, so that since we had since we need for the concatenation part, we need the number of heads in this dimension. So this part is reversed over here, and then this part is reversed over here, and then since transpose of a transpose is a self value, so we are just transposing that, and we are saying the contiguous because we need to transpose into finally batch size, d model, and the -1 is filled automatically, which is equal to sequence length. Very simple, right? So only thing that we need to understand is that given the d model, we need to decompose into two parts, this and this, but the self attention, this scale dot attention expects this dimension to be sequence length, so we need to transpose that, and the return value also returns the value as expected, but we need to put the sequence length over here, so we need to transpose that again, because we had transpose over here. And the output of this is sequence length and dv, and although this is a sequence length that is a transpose that's returned by the scale dot product attention, we need to convert it into previous form, and then finally pass to attention output layer, and the output is output. Okay, so that makes complete the multi-head attentions. This position wise input feed forward is very simple. There are two linear layers. First pass to linear layer, pass to ReLU, apply some dropout, pass to second linear layer, simple. Finally, the encoder layer is first to the self attention of itself, query key value itself, and then pass some normalization and this residual connection. Finally, pass to this residual connection over here. So this thing is this add and norm is this form. This multi-head attention is this. Okay, this is this. Finally, the feed forward x is this value, and then add and norm of this is this residual connection. Finally, the output is return x, and this is a one encoder layer. So this one encoder layer, and same goes for the decoder layer. So there is some cross attention from extra layer, and what happens is very simple. Self attention this value, but we need to do the target max also. The max is also passed, and this normalization, finally cross attention over here. The cross attention is very nice here. If you can see, attention requires query key value, and query is itself the keys and values are from the encoder output, and the source max from the source max. Okay, and add and num this value, finally feed forward and add and num. Okay, so encoder layer is if you can see, encoder layer is there is some embedding and positional encoding, so n number of layers and dropout and demodel. So first pass to embedding, the embedding also is scaled and then that is the embeddings are passed to positional encoding, and for each layers in layers, the output of layer is okay. So for the first case, x is just input. For the second case, this is second case, the output is itself. I mean, say input first pass x from the input. For the second, this value, computed value, is passed over here. The recurrence relations output of this fed to itself for number of layers times, and decoder is very tricky, somehow tricky. So the encode embedding and this is very similar, but uh, for the first part, x is same, and the encoder output is same for all cases. So encoder output is same for all the layers. Encoder output is same for all the layers. Okay, the encoder output is same for all the recurrence relations. This n number of times the encoder output remains same, and same is for source max and target max. And finally, the transformer has some encoder and decoder and some projection output, final layer, and parameters initialized with Xavier uniform. This is this formula. Okay, let's now go to the forward. Encoder output pass to decoder, and then finally project it, and the output is returned. Okay, so that's marks the implementation of the transformer model. And now let's some MQTT functions. So first one is create padding max. Padding max is very simple. If the sequence length is not equal to that, so I think I had done some visualization tasks. So let's go over here, the tensor implementation. So where it is, excuse me, this is over here. Oh, okay. Okay, now where it is. एकछिन है हजुर. So I wanted to show this. So for example, we had this sentence, target sentence in this. I wanted to show this because I want to make clear on this one part, which is very tricky and main component also. The part is in the training report we had this slicing operation, this one. Okay, in the evaluator target report we have this operation. So let's see what this means. So if the target input is this, right, the token IDs becomes this. Start is 1, end is 2, 0 is pairing token, and the sequence length is 1, 2, 3, 4, 5, 6. Okay, now the padding max, the create padding max function in our this function would return this value true, 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 false, because only this 0 is false, that is over here passed. So padding max means wherever is the 0, make that false, otherwise make that true. And on squeeze adds 2 dimension. For this some sequence length we need one is this one added. Okay, this one adds, so the best dimension is final one. These are for the broadcasting operation. We need these dimensions, the 4th dimension as required in the multi-head attention. So, and the create lookup max is much more trickier. So this create target max for this is much more trickier than the previous one. This is because the first one we need to create the max function. So diagonal equals to 1 would return this value. So for each diagonal equals to 0, for this diagonal equals to 1. So from this diagonal, that is 1, it's all 1. So from, and this is upper triangular, but the diagonal value is 0 because we have passed diagonal equals to 1 over here, positive value. And then finally we are again passing the max equals to 0 in our function. In this function, if you can see, this as first create the this lookup max as first we need to create the triangular matrix, and then setting max equals to 0. So basically this would become true, 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 true. So this would becomes true, 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 and above this and above would become false, which means that first see the first word, second first and second words are allowed. For the third part, first, second, third words are allowed to see, but the futures are permitted to see. So this is kind of very interesting thing. And finally, this is just the dimension expansion for the broadcasting operation, and this would do something like this. So the final output becomes something like this. So we are not seeing anything from the future, and if it's some padding index, we should not attend to, then that also becomes 0. That also becomes 0. This was padding index, so it becomes 0. And the main final thing is, and apart from that, there is some extra thing that I needed to show you. This one, okay. So I try to show you how these three utility functions works. Now finally, it's time to understand. It's time to understand the train epoch part. What is the train epoch? It's all the way down. Okay. Sorry, I just need to search a train epoch. So here we are doing these two operations, which is very crucial, because let's assume we have this sentence 0, 1, 2, 3, 4, 5. These are decoded position. So this is a token. Now the target output, this value, target input. Okay, the target input is removing the last token. So this is removing the last token. Whatever is the last token, just remove that. We don't care if it's bad, if it's EOS, if it's whatever it is. In the worst case, in most of the case, it can become EOS, but for other cases, it will become bad. So we don't consider whatever it is. We just need to. We should not take the last token. So we had. So it removes the last token. So we had two paired tokens. Now we just have one paired tokens, right? So we are just ignoring the last part, last token. Finally, the target output, the target input removes the last token. It removes the first token. So whatever is the first, it was start of the, so always is the start of the token, start of the sentence, and that is removed, and we have entire thing. Now if you align this, what happens is that, so decoder input becomes SOS. So it has not one sentence, it has not one token, it has not start token. So now you can clearly see this. From given is SOS, we need to compute this word, this token. We also have some encoder output also, but point is that given this, predict this, given and this output is fed over here as kind of auto regressive manner, and given this and also the encoder output, predict next word, and this predicted word it auto regress to next part and also combines the encoder output and predict the next word. So given this as output, take that as input and predict next word. Given this predicted word, take that as input, again predict next word. So it's kind of, see, this. So this is a kind of auto regressive manner, but it's not doing in the classical RNN manner. So it's not doing in the sequential manner, it's doing in the parallelized manner. So it's just doing the one matrix multiplication, and boom, it's kind of doing all this loss function and all this prediction in a one go. So it's not doing sequence manner. So that's the power of transformer. And so this ChatGPT explanation understands us this two crucial inputs and then these two crucial utility functions, and that marks the end of our explanation of the transformer model. And so where it is, okay. So thanks for watching. So this was the explanation for the transformer model, and so summary is very simple. First one is how the scale dot product attention works, how the multi-head attention works, why they choose multi-head attentions, why not simple one attention, and then finally the parallelizations that was visible in terms of multi-dot attention as well as the decoder autoregressive part. So although it is autoregressive part, it's not serialized as in case of sequential, as in case of the RNN. It's highly parallelized, totally parallelized, and that's the power of transformer. And then finally, um, we understand how the masking works. So there's a two kind of masking. The for the simple, we don't want to give attention to paired sequences. Also, we don't want to attend paired tokens. Also, we don't want to give attention to future tokens in case of the decoder layer. So for that, we need to do the triangular matrix, and then so triangular matrix is very simple. It is not saying the future values. Mm, just we just need to see that the decoder maxing is just a triangular function multiplication to encode, so that the future values, the values that are from above from the diagonals are multiplied with 0, so that they become 0. Let's say the softmax predicts 0 probability for that, because the masking would makes anyways, that's simple. So for the decoder masking is just a triangular matrix, right? And then what's complication? So basically someone would be confusing about multi-dot attention. So why does that work? And this is very simple. So they are just doing the physical significance of the three vectors, the query, key, and value, and the significance of the self attention and self attention in case of encoder and decoder, and then cross attention in case of encoder and decoder. This can be understood in very simple manner. So basically, the thing is that there are three vectors, right? Q, K, and V, and we can and in its most basic form, these are some three vectors. So these are not three vectors. So query is the vector. Query is a single vector. Keys and values are matrices. So uh, um, for the self attention, it try to make so it tries to you know uh, do the multiplication with for this kind of for this QKB multiplication physical impedance, I think I need to make separate video, and for that stay tuned, and I will be discussing in depth about what's the physical the significance, or what's happening actually in the QKB matrix multiplication. uh, but for now, let's understand that the QKB in transform model are just three matrices that are multiplied in some in first taking the Q and K and multiplying that, and then taking the probability, and given the probability, we are just multiplying that to the values of matrices, and that is the output of the the attention. So that's attention. So it's not the attention new for in case of the transfer model. The only thing that's new in transfer model is that there is no RNN and CNN, and everything is transfer, everything attention. That's the new. But attention thing was developed prior to this transfer model, and uh, this uh, so I think that's all for the transformer implementation, transformer paper review, and all. So if there's any questions, please ask in the comment section. So thanks for watching. Bye bye.